Here. So, dear students, this is going to be the continuation class of the complex formation. So, as per yesterday's notes, what we have seen is log of Zn2 plus is equal to 10.9 minus 2pH, right? Question number 1. Number 2, log of Zn OH 1.05 minus pH. Number 3 is log of Zn2 plus ZnOH2 is equal to minus 6.95. Number 4, log of ZnOH3 minus is equal to minus 16.89 plus pH. Number 5, log of ZnOH42 minus is equal to minus 29.58 plus 2pH. So these are all the equations that we derive after the formation of complex using the solubility product values. Okay, so now the next step, what we have to do is, we have to draw the graph between, the log concentration this is going to be log of concentration. This is going to be pH. Okay. So first thing is, say for example, you have to find the graph of Zn log of Zn. So say for example, if pH is equal to 1, log of Zn will be 10.9 minus 2, right? So let me just give you a rough idea so that I can make a shortcut. Say this one, or what you can do is, you can do here over here. Log of Zn2 plus, log of ZnOH plus, log of ZnOH2, log of ZnOH3 minus, log of ZnOH42 minus. And this is pH at 1, say maybe 2, 3, 4. Okay, it has to be calculated. Say for example, you see here at pH 1, log of Zn will be 10.9 minus 2, so it will be 8.9. So this value will be 8.9. Okay, then what about this one? At pH 1 it will be 0.5. This will be minus 6.95 constant. This is at pH 1, minus 17.89 plus 1 will be minus 17.89. Okay, minus 17.89. This one will be 31, minus 31.58. If you got what I'm saying, this is at pH is equal to 1. So that way, now let me shortcut. If I keep on doing it, it will take a very long time. And say for example, at pH is equal to 6. I'm just giving one example. At 6, 2 6 is 12, 10.9 minus 12. Okay, it will be minus 1.1. If this is 12, so 12 minus 1 is 11. So this will be minus 10.95. Minus 6.95. Correct? If this is 6, No, no, this is not correct. 6. So this is a 4.95. And about this one, if this is 6, that will be minus 10.89. If this is 6, 2 6 is 12, minus 12, sorry, plus 12 and minus 29. So it'll be minus 17.58, correct? So this way you have to calculate for all the pH 1, 2, 3, 4, 5, 6. You have to calculate say probably around pH till pH 14. pH is equal to say 14. In pH 14, this value will be 2 14 to 28. So minus 20, so minus 28 and 10.9. So it will be this. So the value will be 11, 17 minus 17.9. 17.1, right? Correct. And this one is, if this is 14, minus 14 plus 1, minus 12.95. This is minus 6.95. This one is 14, so this will be minus 2.89. 14, 28, so this will be minus 1.58. Is the concept clear, I think? So using this, we are trying to find the concentration of all these species. These are different species of the zinc. So for all different species of the zinc, we are finding what will be the concentration at different pH. We estimated it. Is it okay? Let me look. The video is still there. Fine. Okay. So this way you try to estimate for pH 1 to pH 14 for all the species. Okay. Then using these values, we are going to draw a graph. So let me draw the graph in the shortcut. Okay. Okay, so the rough graph what I have already is fixed with me. So for me, pH 1 is not very important. Let me start with pH 4, 6, 8, 10, 12, pH 14. The first log of zinc. This is logarithm of the concentration. The concentration may be either zinc, zinc hydroxide, zinc OH2, zinc OH3 minus, zinc OH42 minus. Different species we are going to draw the graph. Simple thing. Log of ZnOH2 is going to be minus 6.95. So over here, maximum will be from 0. So you make it 0, minus 1, minus 2, minus 3, minus 4, oh, this is going to be a little bit smaller. So let me make it from here. Minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, here around minus 8. Okay, these are your minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. So for ZnOH2, ZnOH2, this one, it is minus 6.95. This is minus 7. So probably The graph will be minus 6.95, means it will be here. This is log of ZnOH2. This is constant irrespective of any pH. Correct? This is one. Or simply you can say this is the graph of ZnOH2 species. Okay. For a Zn2 plus, the graph comes Zn2 plus. Which one is Zn2 plus? Zn2 plus is coming something like this. I'm directly copying from the existing graph, that's why I'm making it. Okay. Say for example, at different pH, these are the values. These are the values at different pH. So what we do is we draw, this is Zn pH. So this is Zn2 plus. Okay, fine. The next one is ZnOH. All these values are drawing by using the tabulation table that we have done just before. For ZnOH plus, this one, ZnOH, we got it like this. ZnOH plus is minus 4 minus 3, and then it comes to around 10. And this is ZnOH plus. Okay. And then next one is ZnOH3 minus. ZnOH3 minus is from number 8, it is going to minus 5. Okay, this one is ZnOH3 minus. Okay, so to make a little bit difference, you can make it understand like this also. Okay, the last one is ZnOH4. For ZnOH4, it starts from here around, and then it ends in minus 2. Okay, this is ZnOH4 2 minus. Is it okay? So we have 5 species. All the species are, this is number 1 graph, this is number 2 graph, this is number 3, this is number 4, and this is number 5. Okay, so you got the 5 graphs. Now, listen over here. The total will be, the final plane will be, see look over here. Look over here. This is a graph for ZnOH plus at different pH. This is a graph for Zn2 plus. This is a graph for ZnOH3 minus. This is a graph for ZnOH4 2 minus. This is a constant ZnOH2 because it is independent of the pH. Okay, so after this, what happened is this draw a graph like this. Okay, this black is nothing, it is the CT. and here this is the insoluble. This is the precipitation. All this remaining are soluble form. Okay, so this John, this John, this John, all the John, or I'll write on here, all the John below the blank line is soluble. That means the species are in soluble form. Number one. Number two, the John above the black line are insoluble. That is the precipitation form. Some sound is coming. Okay, is it clear? So this part are insoluble. Is it okay? Have a look. I'm going to continue the class. Let me rub this part since already you have copied it. Now by looking at this graph, we are going to discuss, this is a final graph. This is called the log concentration graph of zinc at different pH. This is called log concentration curve of zinc hydroxide. We can make this one for zinc chloride, zinc sulfate, whatever. This is for zinc hydroxide. Why hydroxide? Because I explained in the last class. We are trying to precipitate by using the hydroxyl ions, all the heavy metals, and then we can remove the heavy metals. Okay, so from now on, we know that all the John that is above the black, this is the insoluble part. This is the final touch, the black one. Okay, you see here. From this point, what we learn is that, number one, what are the conclusions we draw? The minimum solubility. Minimum solubility of zinc with hydroxides occurs at, you see, at what pH the minimum solubility happens? At what pH? From the graph, it seems like it is occurs at this point. This point, correct? And this one is pH 9.4. So occurs at pH 9.4. Okay? Is it clear? The minimum solubility. Okay. So at pH 4, number 2, what is the concentration? And total equilibrium zinc concentration is how much? At pH 9.4, this is the equilibrium concentration. And what is this value? You bring out here. From the graph, the value happens to be The concentration is this part, this concentration, correct? This is minus 6.79. Actually, I'm not able to see in the this minus 6.79, correct? So this concentration is log of minus 6.79. Okay, not minus 6, but this is log of minus 6.79. This is equal to, this is equal to 1.6 into 10 to the power minus 7 moles. From the graph, we obtain that the value is minus 6.79, correct? The minimum elicibility at pH 9.4. And if this, the value of logarithm of the x, say the log of x is equal to minus 6.79, therefore x is how much? Therefore x is equal to 10 to the power minus 6.79, correct? This is equal to 1.6 into 10 to the power minus 7 moles. So the concentration of the zinc for the minimum solubility is 1.6 into 10 to the power minus 7 moles as per this graph. Is it okay? Now we are going to solve one problem. Okay. All these concentration are drawn in the log concentration. So the value is log of x is minus 6.79. Therefore x is how much? 10 to the power minus 6.79. So it is 1.6 into 10 to the power minus 7. Okay. Fine. So have a look again. Now we are going to find a new questions. Have a look. I'm just giving for a few seconds. And you can say from here also that the predominant species is, at this point, this is the predominant species. ZnOH2. ZnOH2 is the predominant species. Okay. Now you can say at pH 6, I'll just give an example. At pH 6, what is the minimum value? You can find here, this one. So this is the minimum solubility. What is the predominant species? This one, that is Zn2 plus. Okay. So let me drop this and let me give you some other examples. Now, say let's say at you want to precipitate at pH 6. You said, sir, I want to precipitate at pH 6. I can maintain at pH 6 because the effluent I have to use for a particular job, so I don't want to make it very, very basic pH like 9.4. I want to precipitate at pH 6. Or another example is you said, no, sir, I want to do it pH 7 because after the treatment, I want to use the water for other purpose after the removal. So I want pH 7 neutral pH. I don't want acidic nor I want basic. Then the thing is, what will the value of the concentration at pH 6 where it will get precipitated? So if pH 7, then you can say this is pH 7. Then at pH 7 you can draw the graph. My graph may not be exactly accurate. So this is the pH 7. Okay. So at pH 7 you have to find this value. I don't know maybe exactly correct or not because my graph is not very accurate. So what you can say is at pH 7, say for example, it is around, what is this value? This is minus 1.7, say for example. Okay, at pH 7, the log concentration is equal to minus 1.7. Therefore, concentration of the zinc is equal to 10 to the power minus 1.7. It's equal to how much? If this were in the class, some of you can tell me the value. 1.7. 0.12. 0.012 moles. Okay. See, the concentration of 0.012 moles is very high. So you have to increase the concentration of zinc by so much mole so that you can precipitate at pH 7. So if you increase the concentration from this one, the zinc concentration, then you will get precipitate. Okay? But the thing is, you may ask me, sir, in order to remove it, why should we increase the concentration? Right? So my question is not based on that. My point is, if your concentration is higher than 0.012 moles of zinc, then it will get precipitated at pH 7. Is it okay? So that is the basic concept. And if you try to find what is the molecular weight of zinc, (65.4). Molecular weight is equal to 65.4. Correct? That means 1 mole is equal to 65.4 grams. Therefore, 0.012 moles is equal to 0.012 into 65.4. It's equal to how much? 65.4 into 0.012. That is 0.784 grams. So this is 784 milligram per liter. So if the zinc, so that means the zinc concentration of around more than 784 will always get precipitated at pH 7. If it's 800 milligram per liter, it will get precipitated. Is that clear? That is the basic concept from this graph. Or in other way, and another one is the predominant species. What is the predominant species? Is this green color. This, what is this green color? This green color is Zn2 plus. Is Zn2 plus. You can see this green color is a graph of Zn2 plus. So the predominant species will be Zn2 plus, the complex. Is that okay? So at pH 13, the predominant species will be this red color, that is this one. This will be the predominant species. Okay? Now let's do only one numerical, very small numerical by referring the graph. So I'm not going to use the green color, it's very difficult to remove. Say a question is there. A plating industry has waste of zinc 10 to the power minus 3 moles per liter. Okay, if lime is added to increase the pH and precipitate zinc as insoluble, at what pH should it be done? So say a particular industry has got a wastewater having a zinc concentration of 10 to the power minus 3 moles. You go to your industry, you collect the samples, you estimate in the lab either by using atomic absorption spectrophotometer or any device to estimate the zinc. You came to see that the zinc concentration is 10 to the power minus 3 moles per liter. Okay. Now the question is, if you want to precipitate it out, at what pH you should maintain so that you can add lime. Why you're adding lime? So that you can increase the pH. It's one of the cheapest technology. So at till what pH should I do it so that it will get precipitated, right? So here log concentration is equal to 10 to the power minus 3. Therefore, zinc concentration is equal to minus 3. Correct? No. Concentration is equal to, my goodness, this really kills me. Concentration is 10 to the minus 3 moles. Therefore, log of concentration is equal to log of 10 minus 3 is equal to minus 3. Now, you have to see where is minus 3? This is minus 3, correct? So, at minus 3, this part you see here. At this minus 3, you have to bring up to here. Then you have to bring down here. Okay. So minus 3 and then you're bringing down here. So what is the pH? Let me see. This is not accurate. What they are trying to obtain is the pH is from the graph. They obtain that pH is equal to 6.9. Please note it down. It's from our notebook. This may not be exactly correct. Here is 7. Actually, it doesn't seem to be here. It seems to be here. My graph is not correct. Okay. The value is 6.9. From a graph, you get around 7.8. This is not accurate, as I told you. So it is around 6.9. I'm telling you the concept. Okay. 6.9. So pH 6.9 means you should maintain a pH above 6.9, then it will get precipitated. Answer is very simple. To answer it is very simple. The difficulty part is forming the zinc complex and preparing this chart is the toughest part. Okay. Question is very simple, correct? Then another question is, they say, if what about this one? They say you want to precipitate it out. You want to precipitate it out, but you don't want to decrease more than 10 to the power 5. Okay, look here. What this question is, they said zinc is equal to 10 to the power minus 3. You add lime, and then if your lime is there, it is decreased, the concentration is decreased, right? This, what is this? This is precipitation is going on. Precipitation is going on, and then the concentration of the zinc is decreased. And this happens at pH greater than 6.9 by addition of lime. So the concentration will keep on decreasing. The concentration will keep on decreasing. Do you want to remove everything? The question is, say no. I want to maintain till pH 4. Want to maintain till zinc 10 to the power minus 5 moles. Okay. What he said is, I don't want to decrease less than this. I don't want to remove everything, but I want to remove till 10 to the power minus 5 concentration. Then what you have to do is, so you keep on adding lime. So question is, till what pH we should add lime, right? So initial pH was 6.9. What should be the final pH? This is the question, correct? Simple. For 10 to the minus 5, 10 to the minus 5.5, C will be minus 5, correct? So C minus 5, you check here, then this minus 5, then you bring the graph up to here, then you bring down here. This pH. And the answer happens to be 7.9. 7.9. Is the concept clear, everyone? I believe so. So now let me explain once more again. You have a zinc wastewater treatment plant. The concentration of the zinc in your wastewater treatment plant is 10 to the power minus 3 moles. Concentration is very, very high. 0.001 moles. It's very high. So what you said is, sir, I want to precipitate it out. But I don't want to remove everything. I want to remove only till the concentration of 10 to the power minus 5. 10 to the power minus 5. That is, I want to remove from 0.0012, I want to remove till 0.00001 moles. Correct. By addition of lime. So, how do I know that the zinc concentration is achieved? So what I'm telling you is, don't do anything, just maintain the pH greater than 6.9. Keep on adding the lime, keep on adding the lime. Till what pH? Till pH of 7.9. By 7.9, it will come automatically by this graph. Is it clear? That is the basic for number 2. So, we may ask you again, if I want to remove the concentration from this much to this much, at what pH should I maintain, until what pH should I maintain? So that is the question. Is it clear? So this is the way of removal of heavy metals from the wastewater by addition of hydroxides to precipitate. But mind you, don't think the wastewater contains only zinc. There are a lot of other ions that is present in the wastewater. Okay, so this is clear. Let me tell you some more points. Your wastewater contains zinc, and we are trying to make it added of hydroxide, and this becomes heavy and it precipitates, correct? But don't think only hydroxide is present or only you can add hydroxides. In the wastewater, sometimes it may contain chloride, sulfate, some other heavy metals also may be present, correct? So, My target is to mix zinc and OH. Our target is to mix zinc and OH. Other ions are there. These ions are called interfering ions, like chloride, sulfate, any other ions, and especially sometimes NH3 also there, ammonia also there in the wastewater. Fine. Now then you may say, so even if I do something, there will be other more ions. Yes. Being Mtech students, we are just trying to teach you how to make the low concentration curve. Now the thing is that if there are other ions present in the wastewater also, we have to make the complex formation between the zinc and the chloride. You have to make zinc sulfate. Everything has a complex formation, solidity present. We have to add and we have to subtract a lot of things. That is not in your syllabus. Your syllabus is the basic fundamental of formation of complex ions and how we evaluate. So the formation of other complex ions along with the chloride, sulfate, all these things, that is actually in PhD for a particular research field. Okay, so if any doubt, we'll discuss further during the introduction program. Thank you very much.